Imagine sitting in your Physics 0625 exam. You perfectly understand static electricity, you write your answer, but results day hits and you've lost an entire grade boundary on a seemingly basic electrostatics question. Why? Because you didn't legally steal the examiner's mark scheme. In this explainer, we're pulling off a mark scheme heist. I'm going to show you the exact hidden tripwires that are destroying your scores and give you the blueprint to perfectly engineered answers. Let's go. So picture this. You're in the exam hall, the clock is ticking down relentlessly. You turn the page and see a question about a simple static electricity experiment. You know, rubbing a plastic rod with a cloth. You literally smile, right? Because you know this stuff. You write down your answer feeling like an absolute genius. But here's the painful reality. Thousands of confident students hit a hidden security tripwire right here and lose 3 completely avoidable marks. 3 marks! That's the difference between an A and an A star. It happens because knowing the physics concept is only half the battle. If you don't speak the exact, highly specific language the Cambridge examiner demands, your knowledge is basically invisible to them. Let's look at exactly what went wrong. Check out this answer. A student wrote, "The polythene strip became positively charged because it gained positive protons from the cloth when rubbed." Now look closely at that phrasing. This is a massive, massive trap, and ordinary revision fails here, because to the untrained eye, the logic kind of seems to hold up. You think, well, if it's positive, it must have gained positive things, right? Absolutely wrong. This exact sentence earns 0 marks. The examiner's red pen will literally slash right through it. Why? Because it's the ultimate physics cardinal sin. Protons are locked deep, deep inside the nucleus of the atom. They do not move during simple friction experiments. Writing this tells the examiner you have a fundamental misunderstanding of atomic structure. Standard textbook reading doesn't warn you about this trap, but mark scheme thinking does. To completely bypass this trap, we need our first quick win. We need to remember the absolute golden rule of electrostatics. Only electrons move. That's it. An electron is a subatomic particle carrying a negative charge, and it is literally the only particle that can be transferred by friction. When you rub that cloth against the polythene strip, the friction provides mechanical energy. That energy is just enough to strip the loosely held, negatively charged electrons from the surface atoms of one material and transfer them over to the other. The key takeaway you need to burn into your memory right now: never ever mention moving protons. Friction transfers electrons. End of story. So the crucial point here is understanding how this one-way transfer actually affects the overall charge. It's like a giant microscopic balancing act. If a material gains these negatively charged electrons, it now has an excess of negative charge, so the entire material becomes negatively charged. Makes sense, right? Conversely, if a different material loses those electrons during the rubbing process, it's suddenly left with a deficit of negative charge, meaning its fixed, stationary positive protons now outnumber its electrons. The result? It becomes positively charged. It's all about who gained the electrons and who lost them. Now in a moment, I'm going to show you the examiner's clue that changes your practical answers completely, a clue that easily saves you 2 marks. But first, you need the framework that makes that clue obvious. And it starts with the foundational laws of electrostatics. Look at this rule set. You have to write this down and memorize the precision of this wording. 2 negative charges will repel or push away from each other. 2 positive charges will also repel each other. But a negative and a positive charge, they attract. Like charges repel, opposite charges attract. You need to know this cold because this is the exact scientific reasoning you'll use to directly back up the physical evidence you observe in the lab. Okay, let's step into the lab and look at the exact method for this practical investigation. This is pulled straight from the standard Cambridge apparatus setup. Step 1, we rub a polythene strip with a cloth to charge it by friction. Step 2, we support the strip horizontally in a little paper stirrup. Now, pause for a second. Why paper? Because paper is an insulator. If we used metal, the charge would just conduct right through it and leak away into the surrounding environment, ruining the whole experiment. And step 3, we suspend it freely from a retort stand using thread. This setup is absolutely crucial because the paper stirrup allows the strip to swing freely. It takes those invisible electrostatic forces of attraction or repulsion and makes them highly visible. All right, here it is. Here is the ultimate examiner clue I promised you. Before you bring another charged strip anywhere near our suspended one, there is a vital, non-negotiable step. You must make sure the suspended strip is completely stationary. If you don't wait for it to stop moving, your evidence of attraction or repulsion is completely invalid. Think about it from the examiner's perspective. If the strip is already swinging around because of a draft in the room or because your hand shook when you let it go, how can you definitively prove that the movement is caused by an electric force? You simply can't. The examiner desperately wants to see that you understand the necessity of controlled variables. Mentioning that the strip must be stationary is a massive green flag that you know exactly what you're doing. Now, if the exam paper pivots and asks you how to actually detect these charges, or how to identify insulating materials like plastic and wood versus metal conductors, the gold leaf electroscope is your master key. This is an incredibly elegant piece of laboratory apparatus. It consists of a metal cap connected to a metal stem with a tiny, extremely thin piece of gold leaf attached to the bottom. Because gold and the metal stem are fantastic electrical conductors, when a charge is applied to the cap at the top, the electrons move and the effects can be seen all the way down at the delicate leaf. It's a classic, highly testable piece of equipment, and understanding how it works is absolutely essential for the 0625 syllabus. Okay, so how do we take all of this physics knowledge and package it so the examiner has absolutely no choice but to give us full marks? We use what I call the ultimate answer framework. This is the core of our heist. Step 1, you state the concept. For example, explicitly mentioning electron transfer. Step 2, you state the evidence or data you observed, like clearly stating attraction or repulsion. Step 3, you provide the scientific reasoning. In electrostatics, this usually means identifying friction as the cause. And finally, step 4, you wrap it all up in precise examiner wording. When you structure your exam answers using these 4 pillars, you literally leave zero room for the examiner to deduct points. You're giving them exactly what's on their rubric. Let's test this framework. I want you to pause for a second and look really closely at this student's answer. Can you spot exactly where the examiner is going to deduct marks for vague wording? The student wrote, "I brought the rubbed cellulose acetate near the suspended polyethylene and they move together because they are charged." At first glance, it sounds like a decent real-world observation, right? It sounds like what you'd actually say in the classroom. But remember our framework. Move together is not precise scientific evidence, and because they are charged completely lacks the deep scientific reasoning the mark scheme demands. It's way too casual. Now here is the examiner-style correction applying our framework perfectly. Compare the vague wording to the precise correction. Instead of using the vague phrase, moved together, our top band answer says they attracted each other. That's the specific scientific evidence. And instead of the weak, incomplete phrase, because they are charged, it specifically details because the cellulose acetate and polyethylene hold opposite charges. Do you see the huge difference there? The accurate phrasing uses the specific terminology that proves to the examiner you deeply understand those core rules of electrostatics we covered earlier. That is how you secure the marks. Let's lock in our expected data for the core practical investigation. Look at this table. If we have a suspended rubbed polythene strip and we bring a second rubbed polythene strip close to it, our observation is that they repel. Why? Because identical materials rubbed with the exact same cloth will gain the exact same type of charge. Like charges, repel. But if we bring a rubbed cellulose acetate strip near the polythene, they attract. This proves that rubbing different materials, acetate versus polythene, results in different charge outcomes. One became positive, the other became negative. Which brings me to the magic number you need to keep in your head, 2. Always remember there are only 2 types of electric charge at play here, positive and negative. That's it. Keeping this simple fact in mind keeps your reasoning completely focused. There is no mysterious third charge to worry about. Whenever you are evaluating a static electricity problem in the exam, boil it down to this binary reality. Either the materials have the same charge and they repel, or they have opposite charges and they attract. Keeping the number 2 in mind prevents you from overcomplicating your analysis when the exam timer is ticking and the pressure is on. So before you finish your exam question, before you even think about turning the page, I want you to run your answer through this, the examiner's red pen checklist. This is how you ensure you've safely secured every single available mark from the vault. Ask yourself, did you explicitly state that electrons are transferred? Did you identify friction as the cause of that transfer? Did you specify which material gained or lost those electrons? Did you clearly use the words attract or repel? And if you're describing the practical setup, did you mention the crucial need for the stirrup to be stationary first? Check these 5 things off and your answer is practically bulletproof. But our heist isn't over yet. We've cracked the vault for electrostatics, but what happens when the examiner throws a completely different question type at you? We need an escape tunnel. I'm leaving you with a final challenge to test your new framework. If you bring that positive cellulose acetate strip near the metal cap of a gold leaf electroscope, how exactly would the delicate gold leaf react? And fundamentally, why? You have the tools to answer this now. But to verify your answer and to discover the traps hiding in calculations and data analysis questions, you must take the next step. Watching our next explainer on Physics 0625 Common Traps by Question Type is mandatory to complete your strategy. Subscribe to our YouTube channel Ace the Exams on the @acetheexams_IGCSE to excel in your Cambridge examinations. Click the image on your screen right now to jump into the escape tunnel and master the rest of the syllabus. I'll see you there.